All right, kiddos, I don't know if anyone is out there. I just started going live. Sorry, I'm technically 2 minutes late. Been trying to get this thing kind of working. I'm sending out a quick email to all of y'all. To the BC kids anyway. This is technically the BC hour. AB kids, if you're on here right now, you're going to want to come back at 11 o'clock. Or I guess you could listen to the BC packet, but it won't specifically be helpful to you. I did check my Google Doc, I think at 8:15-ish today, but I think I probably have live changes. So if anyone did not go in the Google Doc from the email, to post what questions you had. You might want to go ahead and do so now. I did have quite a few, not quite a few, but I did have some questions from Isa. Isa sent me in questions, so I will go ahead and go over those questions. Sending out a quick reminder. There are, I think, quite a few BC kids that have not yet sent me their commitments, so they're not in my contact list. Live study session on now. More questions on the summer packet. Let me get my link just to put it in the email in case some of you guys, well, anyone listening to this video, you already figured it out, so you're totally fine. But for those of you that have not joined and wanted to, I'm just trying to send them really quickly a reminder email, just in case they did want to join. All right, I know quite a few of you guys are out traveling for the summer, so you might be listening to this video at a later time. If so, that is totally fine. Just make sure you read carefully the directions in the email that I sent. And if you're watching this because one of your friends told you that you needed to do it and you still haven't sent me your commitment email, please, 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 please email me so I can get you in the BC Calc study list. With that, I have just pulled up my Calc BC summer packet questions again. So far, I still only have Isa's responses that have been listed, which is totally fine. So I'm just going to go through and order the questions that he had on the BC packet. Some of you guys might have friends that are taking AB this coming year, and you know what their summer packet is already like. I mean, if you want to get tutoring hours in even before the start of the school year, as long as you document it the way you know you should, I'm totally for that and not against it whatsoever. So that's a cool idea too. I have a viewer, but it might just be me. I'm not really sure how to see who my viewers are. I don't know either. Okay, so here we go. Isa, if you're watching this later, thank you for submitting your questions because that gave me stuff to go over today. And if I didn't have stuff to go over today, well, I guess I would just cancel it and then come back on at 11, which might have been kind of nice, but that's okay. Happy summer, everyone. Hope that it's been going well. And email me. I will have my Gmail open. So if for any reason you can't comment on the video, feel free to email me and I'll see your questions pop up that way. Sometimes you can comment and I can see it pop over to the side, but sometimes you can't. Yeah, there we go. All right, everyone. Here we are. Okay, Isa's first question was Calc BC summer assignment. There we go, 2018. From what I can tell, it was number 8. Let me get to where I can actually see his questions. I can split screen this puppy. Let's throw this guy over there. And let's throw this guy over here where I can see the questions. Okay, his first question was number 8. So for number 8, getting to it in the packet. I should not be in green. There we go. Number 8 was talking about composition of functions. Whenever you see that little O, making sure I'm in the right document, I'm not in AB. This is definitely BC. Good. So for number 8, if you guys check out the composition of functions, let me just make this really large so I can write it a little bit better. Another way of seeing this, or another way of viewing it, that I think is a little bit easier would be, not like the width of that marker. I apologize. Give me just 1 second. There we go. I think for you guys, it would make a lot more sense if it was G of F of X, like this instead. I think that's a lot easier. And then all we have to do is think about compositions of functions. We always start with the innermost, since we don't have like an f of 3 or f of 5. We just take the f of x function you guys can see up here, right up above, which is the square root of x minus 3, quantity x minus 3. We're going to be plugging that into the argument of g of x. Remember, it replaces the current argument of g. And so it's going to be just like the following, plugging in that x minus 3 into g's equation, which is quantity squared, so f quantity squared plus 5, which you guys remember from last year. You could stick it to the man, but if you want to be super snazzy and have it match the answer key, I'm pretty sure I would go ahead and just square that square root, and so I'd have x minus 3 plus 5, some quick mental math, which is hopefully correct, would be that quantity x plus 2. We could go ahead and double check. I was going to have the key open also. Calc BC key, there we go. And so then for number 8, dun, 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 that is correct. Why I have this extra little qualifier right here is because of just the natural argument of the function f. Because in order for f's outputs to get plugged into g's inputs, you have to think about f's domain is restricted. And so I just put that little extra qualifier because for f's, sorry, I got an email in my Gmail, but it's actually from a Calc AB kid, so I'll go ahead and wait on that. In order for an input to work in f, x had to be originally greater than or equal to that 3, just because of the limited domain of the square root function, which hopefully we're all good on. So that was our little such that was going on in the answer key as well. Okay, Issa's next question was, remember, email me if you join this and you have some questions and you didn't submit your form yet. The form was just a link in the email that I sent out to you guys announcing the summer sessions and letting you know that I could be going over questions. And so there's just a form you can go in and just check box the numbers that you got stuck on. We're going to number 22. You guys missed my noises, I know you did. Aha, an exponential function. I'm going to zoom out real quick because I'm going ahead and circling and saving these notes for later. That way on the next study session, I don't just explain the exact same ones over again. But for number 22, we have, I think it's a t, yeah, solve for t, which is stuck in the exponent of this little function right here. Hopefully you guys remember the easiest way to break down an exponential function is using his inverse. And his inverse is a logarithmic one. And hopefully we all remember from last year, ln is so much easier than any other log. So I'm going to go ahead and just take ln of both sides. And in taking ln of both sides, making sure my sound is turned up really quickly. I didn't think to double check that really fast. There we go. Okay. And taking ln of both sides, we are able to, using the logarithmic properties, bring that exponential, or that exponent, I should say, down. So we are going to end up with t ln of 1.045 equals ln of 2. Hopefully you guys notice with a simple division, we're going to totally have that t isolated. Some of you, just a couple, might be like, hey, I remember there's that really cool property of ln's, like multiplication, division can be rewritten as stuff. There are properties, but go back and review either your pre-cal or your AB notes, because neither of those properties apply right here. That's only if you're doing a subtraction of two separate ln's or if you're doing an ln of an argument with division. But this is two separate ln's being divided. It does not fit in the properties. Go back and check those out if you wanted to go further. Checking out the answer key real fast to make sure we're good. Number 22. ln of 2 over ln of 1.045. If you had a calculator, sure, get a decimal, but stick it to the man. That's the answer. You're fine. We're good to go. I'm jumping to number 28. It's the next question that I see. Has to do with investment. This is very much a pre-cal question. The nice thing is we're not going to really have to memorize any of these interest formulas for Calc BC. I don't want to make you guys think that you need to, but we will be dealing with, as you guys remember from last year, word problems that could include financial stuff. So just kind of having us peek at one of these formulas, compounded quarterly. Sadly, that is not going to let us use that nice compounded continuously. That is just e to the RT, that's the one that we like. That's a simple exponential growth equation, but that's compounded continuously. So for this one, you'd actually have to go back and remember the formula for interest has to do with, let's see, n compoundings per year. If I was an amazing pre-cal teacher, I would totally remember exactly what chapter this came out of, but I don't. It was when we were talking about logistic, though. We talked about logistic equations, exponential equations. Pretty sure it was first semester, but I might be totally wrong on that. And like all these different types of growth. Anyway, long story short, there is a formula for that. If we go ahead and look, we can peek. And I actually have it kind of nicely written out here. It's not super gorgeous and super pretty in the sense of I didn't write it super nicely. But I can write it here. That's our little equation that we're going to be using. And once again, not something that I expected you guys to have memorized, but to see if you could be resourceful and go find it. So this one is going to be I, which is just the interest. Or I could just say y to be a little bit easier. Y is equal to, I think y is technically the current amount, kind of like exponential growth. Y is how much you currently have after time t. You have p being the principal, what you start with. You have 1 plus, I should remember this formula, r. Yeah, r over n. R being the rate of the account, n being the number of times it's compounded per year. And then you have to the power of n times t. And once again, the number of compoundings per year. T being time. And so I just went ahead and took this equation back from the pre-cal days. I know, lame sauce. But I took this equation and I went ahead and plugged in. And that's how I got the, starting off with 2,700, 1 plus, remember 9%, change that to a decimal, so 0.09, all over the 4. When it says quarterly, 4 quarters in a dollar, think there are 4 quarters in a business year, or I should say a fiscal year. So quarterly, that'd be 4 times a year. And then you have that once again, 4 times per year times t. And so if you guys notice, it's saying when will his balance reach a current value of 4,550, which is why I plugged that in. I started to say I, and I apologize, that's incorrect. Y is the current amount of the account. And so then at this point, it's going to be just like number 22 in that you're solving an exponential equation. If I were you going in order, first, I would go ahead and divide the 2,700. Then you would be stuck with this whole expression to the power of 4t, so you need to take ln of both sides to let that 4t come down. Then I'm pretty sure you're going to divide that 4 because he's going to be just chilling in front. Then you're going to want to solve for the t. So you're going to leave the t and divide by the ln of 1 plus 0.09 divided by 4. And I think we'll probably see that right about here. In that, yeah, I totally left it all together. You see the division by the 2,700. You see the ln of both sides to pop this little guy down. Then you see the division by 4. Then last but not least, to get the t alone, you can go ahead and divide by that nasty ln expression. And so I ended up with 5.864 years. You get rid of all that highlighting, kind of messes up the answer key a little bit. Okay. So that one, I'm just going to put a little dot, 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 play around with the algebra. You should end up once again with the 5.864 years when solving for t. I apologize for the 4. It's just getting worse and worse. Okay, so we'll just leave that alone. We got 22, we got 28. We're on a roll. Where are we going to next? It is a big jump to number 48. All right, let's go check out number 48. I'll get the answer key ready. Even and odd, never your guys' favorite. But remember, that's not an excuse to leave it alone. It's an opportunity to dig in and strengthen one of your weaknesses. So, with that, refreshing my email, making sure nothing else has come in. Okay, number 48, algebraically determined. So we're not going to be trying to figure out a graph of this guy. I mean, if you guys really wanted to go through the 15 identifies, that could be fun. 15 steps to a curve, including increasing, decreasing, concavity, points of inflection. Man, that could be a party. But so much easier in that we can just use that old school property from pre-cal that said even, odd, or neither. What we're going to do is we're going to plug in negative x. We're going to see whether we either have f of negative x simplifying to be the same. If so, that's going to be even. Simplifying to be the opposite. If so, that's going to be odd. And then if it's a little bit of both, then it's going to be neither. But you have to be careful in thinking about the entire function. If you're trying to think, does the entire function stay the same? Or does the entire function change? So I'm going to go ahead and plug in negative x. So we can go ahead and say negative x quantity cubed following the pattern of the function. Negative x squared minus 1. If you guys think about a negative raised to an odd power, that is going to end up with a negative quantity. On the bottom, that negative squared is going to remain the same. Now, some of you might be like, aha! Maybe not quite like that, but aha, something switched and something stayed the same. So it's neither. No, it's not neither, and here's why. With division, if I have a negative in the numerator but not the denominator, what does it do to the entire fraction? Flips the sign of the whole thing. You can think about it, a negative divided by a positive or by an opposite over the same is going to be the opposite. So that's why this one would in fact be odd according to my analysis, and the answer key says yes. Okay, checking out the next question past number 48 is number 63. Sorry if you just heard a sigh, that was my dog. Not sure he's quite so excited about math. Not sure I am at this point in time, but that's okay. We're trying to help you guys get through any hiccups, any places in No, Not How to Train Your Dragon, any places you might have gotten stuck. Okay, number 63 is where we are now. We have 0 viewers. Man, you guys are slacking. Okay. Number 63, double checking that was the easiest question, and it was. We have a limit to infinity, so we can be thinking, if this helps you guys remember, we're thinking of ultimately end behavior, horizontal asymptotes, thinking as we go to infinity and beyond. But thinking about horizontal asymptotes, just an xy axis, we're going to the left because of this little negative infinity right here. So we're not going to the right end behavior of the function, we're going to the left end behavior of the function. T is approaching negative infinity. However, we can still think of our degree tests. I'm not sure if I reference this in the answer key. We'll see in a second when we look. But we're going to think about our degree tests. Bottom wins, some sort of infinity. It could be positive, could be negative. Check the sign. There's a tie. Ratio of leading coefficients. Once again, be careful. Check the sign, especially when you have things like square roots. When did I miss? Sorry, bottom wins. I said it backwards. Bottom wins, the function will be having an end behavior of 0. There we go. Then a tie, ratio of leading coefficients. Top wins is when you're going to have that infinite end behavior. Check the sign. So remember, I'm lazy. I'm not going to solve out this entire thing, but I am going to look at, we're going to learn in Calc BC another name for this. But we're going to basically look at the strongest powers, which is going to be that 6t squared. And what's going to happen with this multiplication right here of the negative t and the 2t. So long story short, we're going to actually have a quadratic over a quadratic. There's going to be a tie, ratio of leading coefficients. If you didn't think about it too much, beyond just thinking the degree test and thinking, hey, there's a tie, you would just put 6 over negative 2, and you would say the final answer is negative 3. But remember, I always do say check the signs. This is a pretty basic example. So if you guys figured out last year that you only need to check the signs on more complicated examples like exponential functions are involved, or square roots or cube roots are involved, etc., you might know that it's totally fine just for us to go ahead and box this and be done. But if you didn't realize that from last year, how can we box this and be done and say the sign is okay? If you think about plugging in a negative infinity to the top, you are going to end up with it being squared times 6 plus 5 times 1. Remember, we're just looking at the strongest magnitudes of the top and bottom. So therefore, it is going to be a positive on top all over. And on the bottom, you are going to have 2 times negative infinity, which is a negative, times negative infinity, which is a positive, and a negative times a positive is indeed a negative. There's our analysis, our really, really rough and not very formal, but our analysis of why we're going to maintain the negative on the 3. Double checking the answer key really quickly, number 63. I only do that because it'd be a bummer if in the video one simple little mistake ended up derailing the whole thing. And then I gave you an analysis for a wrong answer. Okay, there we go, negative 3. Next question, as I can see it, would be number 74 and then 81. So going to number 74, checking on my time, and we're still doing just great, just fine. There we go, 74 is ready, and there we go. Circling that one. Let me circle a few more while I'm at it and I'm in the document. I have 74, 81, 86, 95, 103, 104. Hey, unit circle, that was fun. 103, oh, pre-cal. Coming back to haunt us just a little bit, but not in a bad way. Just to make us remember a few things. So some of you guys might want to get out your pre-cal notes if you saved them. And go back, or you can even go online. You guys know I saved my pre-cal notes. I haven't deleted anything yet. I will be clearing out all those folders next week in the sense of homework sheets, class notes, all that jazz. Anyway, you can go back to my pre-cal if you want. You can actually peek at some of the polar parametric. That was second semester stuff. Anyway, we are going to, I got distracted, number 74. Okay, the objective. Find where f is not continuous. Come on, guys, take the wording, not continuous, aka find the discontinuities. And then state which of them are removable versus non-removable. Our simple way of thinking removable was usually they factored out. Discontinuities, you have to consider the function that you're on. For instance, number 73 is continuous everywhere because there's no reason 3x will ever be dne, and there's no reason cosine will ever be dne. Cosine goes on forever, no vertical asymptotes. No breaks, no jumps, none of that sort. But for these two, for both 72 and 74, well, we have fractions, and with fractions, we always look at denominators. And to look at the denominators and to be able to think about removable or not removable, we need to think about factoring. So in this one, factoring, remember, think about what makes x squared, x and x, what makes 10. Well, there's a few different options. You can do 1 and 10. But if I think about how to put 1 and 10 together, and if it will ever be 3, I should say negative 3, the answer is no, 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 no. So I don't like those factors. I'm going to instead use 2 and 5. Looking at the sign that I need to have for that middle term, I need the bigger to be negative, I need the smaller to be positive, and then I can see, hey, that factor is shared. That factor is what we could call, in a sense, removable. So we can say that. We have discontinuities. at x equals -2 and 5. To be a little more specific, let's do this. X equals -2 and x equals 5. X equals -2 is removable because you can see it factors out. And then x equals 5 is non-removable because, as you guys can see, it does not factor out. In the sense of reduced with the numerator, shared factors, and all that jazz. So there's our analysis, and not continuous at -2, removable whole, and it's also not continuous at 5. If we were doing something like domain restrictions, in case you got confused by the wording, if we were doing domain, I would say x could not equal -2 and 5. But since we were talking about discontinuities and identifying, there is a discontinuity at -2 and there is a discontinuity at 5. Hence why I used equal, not equal. With that, let's go ahead and go to our next one. I don't remember exactly what it was, but it was somewhere in the 80s. There we go. Oh, directions. I apologize. Directions are find the, ooh, you guys hopefully had some fun on these ones, reviewing some of your basic rules, but also hopefully whizzing through some of these too. 81. If you were reading this function out loud to someone, you could just say x squared e to the x. Well, that's awkward, that's imprecise. A better way of saying it is x squared times e to the x. And as soon as you say x squared times, what rule should you be thinking of? So, product rule. Second d first, plus first d second. You check it out, remember, if this helps. You're looking at each of the pieces to the sum, and you're saying, is there anything shared? And the answer is most definitely. There's an x that's shared, and there's an e to the x that's shared. Then you say, okay, when I take away an x and an e to the x from this one, if I were to, in a sense, divide by x and e to the x, e to the x's would reduce, only 2 would be left. Let me get rid of all that nasty analysis that messed him up. But the 2 is left. And as we look at this other guy, if we were to divide by x and e to the x would go away. One of the x's would get reduced, but what would be left? X. Always double check by plugging back in, but could you have stuck it to the man way back here? Of course you could, but is this going to be a non-calculator problem? If it's a problem at all, probably not. And if it's multiple choice, they're going to make it nice and neat and simplified. Number 81, I'm just drawing on my answer key. There we go. Oh, I didn't even factor. Well, that's lame. But anyway, there you go. Factoring, I think, is a little bit nicer, to be honest. Number 86, I almost skipped one. Same dealio. You were to read it, x squared times cosine of x, hence why you have second d first plus first d second. Derivative of cosine is, careful, negative sign. And that would be our f prime of x or our dy dx, either way. If you were to make this nice and neat, you would do the same thing I just did of factoring. You would pull out, sadly, only an x to this one, and you would get 2 cosine of x minus one of the x's remains. You took away the other one. There's not really any cool properties like double angle properties or anything like that from trig that's going to make it really look that much different. Once again, you could have left it unsimplified, like the answer key did. Number next one, in the 90s, and I think I saw it down below. Answer key ready. Number 95. Oh, look at this. You're finding a first derivative, second derivative, third derivative. First derivative, increasing, decreasing nature. Second derivative, clues about concavity or about the increasing, decreasing of the first derivative. Third derivative talks about the jerk of the original, which is a little weird, or the concavity of the first, or the increasing, decreasing of the second, but that all is much more than we need to know. So, let's just find us some derivatives. Hold on, double checking this is actually a question. Well, this is a super nice one. Yep, all right. He said if you figure out that you want a different one down, just go ahead and go in and mark it. But I'm going ahead and doing it fast because this is a good old-fashioned power rule. Bring down the 2, 4x minus 3x squared. Second derivative. Power rule, 4 minus 6x. Third derivative. Power rule, oh, it's a constant. Or I bring down the 0 power and that's gone, poof, and then I just get negative 6. Dun, 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 dun. And just double checking my answer key wasn't wrong, and according to what I'm looking at, it looks good. All right, number next one I think is on the next page. Nope, nope. There they are. I know, you guys don't like this one. Did I just... I randomly copied this page and now I don't want it. Can I delete it? Clear page. Not important at this very time. Okay, so instead, let's just go ahead and go over these. So, number 103, graph and show the direction for. Should not be a comma. Oh, it's just like a separating the clause. Graph the relation defined parametrically. Graph and show direction for. Anyway, that's awkward. So we have parametrically. We can tell that because it has a T in it. Remember, I'm saying remember as in I'm just pointing you back to something that you heard before in pre-cal, not that you actually need or should feel bad about yourselves not remembering. But if you can remember, back in pre-cal, we did talk about how parametric equations define the horizontal and the vertical in terms of the third variable t. T is just for time. That's the most basic way to define it, or to describe it. It's the easiest way to think about. Nice thing is parametric equations, there are ways of eliminating the parameter. Eliminating the parameter, we do something like, I would probably just do this, t is equal to y plus 2, go ahead and plug that in. We could get x is equal to y plus 2 quantity squared minus 5. You could think of this as an inverse function of a parabola that shifted to the right 5 down 2, no, backwards, sorry, the inverse of. The inverse of would be to the left 2 and then down 5. And the inverse of a quadratic is going to be a radical function or a square root function. So we could already know this is going to look kind of like a square root function, and we could have gotten y by itself and seen the plus or minus square root and all that jazz. But that's not necessarily what's being needed here, because when we went to parametric and even polar equations, we realized that we don't have a very good natural sense of how the functions look, behave. We don't have them memorized because, I just realized my microphone's kind of far away on my computer while I'm on my iPad. We don't have a very good natural knowledge, understanding of them because we haven't done parametric long, and we haven't done it for a long time also. We haven't done it for near as long as we did function mode. So we could just do a spiffy little like, hey, what did we do back in the day when we didn't exactly know what these looked like? We made tables. They gave us this nice little pretty range. We can say, fine, I'm just going to assume or hope. And from our analysis just now, we realized it was a radical function. You know, radical functions are going to look something, right? But we could also just hope that the values, the nice even values, not using decimals or fractions, will give us a good enough picture. So then just plugging in, thinking t is your independent variable, plugging into the x and plugging into the y and simplifying. It's going to go through pretty quickly. So negative 2 squared is 4, 4 minus 5 is negative 1, negative 2 minus 2 is negative 4. So we have the point negative 1, negative 1, 2, 3, 4. This one. And that's when t equals negative 2, the earliest time in this interval. Because when we graph parametric equations, we have to go in chronological order in the sense of earlier times to later times. Plugging in negative 1, we end up with negative 4, negative 3. Plugging in 0, we end up with negative 5, negative 2. Yeah, just a little bit of a curve going on right here, right? Plugging in 2, we end up with negative 1, 0. Now this is getting interesting. Seems to have made a turn. This is following a path of motion of something. And then plugging in 3, we have 9 minus 5 is 4, and 3 minus 2 is 1. 1, 2, 3, 4. Now we can't draw arrows. That would be improper because our time is restricted. So it started at one time, ended at another, according to our start and stop. It started here and it ended here. So we're not going to draw any arrows as far as going on forever. But we do need to draw arrows for what they said is the direction, show the direction for. So if you guys notice, going in order of chronological time from the earlier times to the later times, go ahead and put these little arrows in to say, hey, this was the movement of the particle or of the car or whatever was on this path. It was going that direction according to our analysis of the time. Number 104. This notation is a little different than you guys have seen before. We didn't necessarily use this a lot in pre-cal. We're going to be using it more in calc with the side carets, I guess you could say. That's kind of how I talk about it. Probably a snazzier name for them, but side carets denote vectors. You could graph these vectors if you're like, I have no idea what these things stand for. Well, these ones, the 2, -1, and the -2, -5, from a point, that's true, 1, 2, -1. But it's showing a direction from an origin. It's showing a vector. So you can go from 0, 0. You can put the tail there, and then you can put the head at 2, -1. It's showing the direction of the vector force, of the vector movement. They haven't really given us an application as to how the vectors are being used. You can also do the -2 and then -1, 2, 3. Now, if you just drew this and said, hey, it looks perpendicular, same thing as orthogonal. Orthogonal is talking about whether or not two vectors are perpendicular. I mean, the way I drew it, yeah, they look super perpendicular. So therefore, sweet, good, perpendicular, let's go. But A, we should probably get out graph paper. B, we should probably get out rulers. C, we should probably get out protractors to actually do it that way and not just take this little ruddy sketch that was not very precise and say, oh, it looks right. We would need to be much more precise to be able to make that analysis. And there still could be some error, like it could be at an 89-degree angle, and our protractor, we probably wouldn't be skilled enough with that tool to be able to figure out the difference between 89 and 90. Anyway, long story short, there's an easier way to do it. An easier way to figure out the orthogonality without going into actually finding the angle between these two, which is a much harder formula, something to do with cosine of theta is equal and dot product and everything. I should have it memorized, but at least I know at the beginning of it. It's much easier to use the dot product formula. And the dot product formula says that we do dot product u dot v, calling this guy vector u, calling this guy vector v. The dot product would be u1 v1 plus u2 times v2. These are talking about the components of the vectors. And so plugging into that, we could say, okay, the u1 of u would be 2, that first coordinate of that vector. And then the v1 would be the first coordinate of the v vector, which is -2 plus u2, second coordinate of the u, v2, second coordinate. Oh, she said horizontal and vertical components, but either way. You end up with -4 plus 5, which is 1, which is not 0. In order to be orthogonal, the dot product, by definition, needs to be 0. That's a lot easier than using that other nasty formula I started to write. If two vectors are orthogonal, the dot products would be 0. If you guys look at the answer key, I don't think I looked at 103 or 104. Thanks for that. But 103, you can see this parametric curve started and stopped, and I showed the direction with those arrows, so that was good to go. I ended up being super snazzy and algebraic and actually got the function, figured out it was a square root function that was shifted left 5, down 2. So I was just being all spiffy. And then I only plugged in endpoints -2 and 3 to get here and here. It's like, hey, follow the motion. Well, wait, -2 went to there. Somehow I had to go from there to there. Then there to there. It must have been traveling this direction. So anyway, I did it in a much more algebraic way, which I kind of introduced to you guys, but I was like, the table works. Number 104, here's me doing the dot product. I just didn't show you the formula. And solving. Since the dot product is 1, which is not 0, let me go back to what I was just doing. Then we would say, but the answer key, but it's not going up. Sorry, guys. I should have written that, but I can put right here. Not, oh, I don't want black. Not orthogonal. If we were to plug into that formula, we would not end up with 90 degrees. And I think the last question, oh no, 2 more. This one was not very specific in the directions that it gave, but find the equivalent rectangular equation and graph. They're like, we don't like parametric. I don't like my brace either, I apologize. There we go. We don't like parametric. So get it back the way you want it, or get it back the way we want it. What's that? Y as a function of x. And the only way to get y as a function of x is to somehow get rid of t, aka this is actually just saying directions from the olden days, eliminate so if you want to go back and peek in parametric, I think it was at the end of the conic section chapter, which I think off the top of my head-ish would be around chapter 10 or 9, I think it's 10. But anyway, eliminate the parametric, sorry, eliminate the parameter is what we're trying to do. Okay, eliminate the parameter is what we're trying to do, which basically just says the parameter, which is t. Go ahead and solve in the x equation. You'll see why in just a second. Solve for t by adding the 3 to the other side. The reason is we're trying to get t in terms of x. So we can go ahead and plug into y to get y in terms of x. We end up with 2 over, who is t, x plus 3. Looking up here at the top, the one restriction I do see on t is that t is not allowed to be 0 because of this little, he's in the denominator of the y expression. If t was 0, kind of translating, if this needs to be true, then I need to go ahead and look over at this equation because that was all from the y equation. I need to come over here and say, okay, hold on, if t can't be 0, then what can x be? Well, x cannot be -3. T cannot be 0, so therefore, plugging in 0, x would be -3. X cannot equal -3, so I would have a quick little domain restriction that x cannot be 3. And that's the full picture of the beginning. What was that, number 106? I did not put the domain restriction. Psh, you should see. Sorry, that was 106. So for number 106, I think it also said and graph. Hopefully you guys remember rational function, basic one, 1 over x. Except in this one, a couple of things have changed. First of all, you do have this x plus 3 in the denominator. So the normal asymptote that would be at 0 has gotten shifted, so it's not there anymore. Instead, it got shifted to the, remember, opposite what you think, which means it was shifted 3 to the left. I have my vertical asymptote. I have my rational function. We can go plugging in things if you wanted, like plugging in -1, plugging in 0. 0 is an easy one, 2/3. Something like that. Plugging in 0, getting 2/3. Plugging in -1, we would get 1. Maybe we can keep on going from there, but long story short, we're going to have our curve with a horizontal asymptote at 0 and a vertical asymptote at -3, and then we're going to have a similar curve or a similar shape. So the symmetry of all these rational functions. Okay, last but not least, number 108. I am not going to do all. Oh, it's a matching one. I always forget what this is. It's matching, so you're supposed to pick the correct letter of what this actually is. Yes, you guys could technically play in your graphing calculator in the sense of something else that you're going to want to remember. At some point, you could go to pole mode, and you could go ahead and you would have your little R of theta, and you would plug in your 5 sine of 3 theta. You might need to play with your window just a little bit. I would probably, if I were you, I would probably also be in depends. For summer packet, I would probably say radian mode. Summer packet, I'd say radian. And then I would do zoom trig. I think those are the settings that I would do if you want to check it out in your calculator. But quick recall. And those of you who are Mr. Chase, I think he did something similar with polar, not making you guys have a nice pretty polar graph all the time to graph polar equations on. You would make a little baby table. Polar is built on angles. Angles, build it on the unit circle. Those are the ones that we can do. If you think about this, there's this little 3 theta dude. And this little 3 theta dude might mess up just a few things. But I'm still going to go ahead and try my normal angles, which are going to be 0. Let me change colors really quickly. 0, pi over 6, pi over 4, pi over 3, pi over 2. I might keep going to 2 pi over 3, 3 pi over 4, 5 pi over 6 pi. And we're just trying to figure out, can we get enough information in order to be able to 3, 4, 5, 1, 2, 1, 2, 3, 4, 5, 6, 1, 2, 3, 5, 2, 3, 5, 6, 1, 2, 3, 5. So I'm going to go ahead and just try those super basic angles of 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, and let's see what we're able to discover. So when we plug these in, 3 times 0 is still 0. Sorry, plugging into the argument of sine. 3 times 0 is still 0. Sine of 0 is 0. So that one's kind of easy. That starts right at the pole. So for the angle 0, we don't go out at all. We stay in at the pole, which is the same thing as the origin, kind of. At pi over 6, 3 times pi over 6 would be pi over 2. Sine of pi over 2 would be, 1. 1 times 5 is 5. So at pi over 6, if you guys remember, 1, 2, 3, you just connect 4, 5. Polar is all about rotating. So we would go out 1, 2, 3, 4, 5 rotations, and we would end right there where the 5th extension out hits pi over 6. We could go pi over 4. 3 times pi over 4 is 3 pi over 4. Sine of 3 pi over 4 is positive root 2 over 2 times 5. That's going to be 5 root 2 over 2. If you were in chemistry, I bet you would have a decimal approximation ready for root 2. Sadly, I'm not that cool of memorizing square root of 2, although I probably should. So if I was to do 2 square rooted on my nifty difty phone, that'd be 1.4. 1.4-ish times 5. Let's do 1.4-ish divided by 2, which would be 0.7-ish. 0.7-ish times 5 would end up being 3.5-ish. So we go out 1, 2, 3.5-ish. There we go. For pi over 3 times 3 would be pi. Sine of pi is 0, so we're back at 0 again. So somehow we've done something to the effect of this. And I know that not all of you are seeing that, but we have. When we go to pi over 2, we're going to have 3 pi over 2 sine to 2 pi to finish off the entire graph. But what's kind of crazy and what's going to happen is it's going to end up just retracing the exact same thing all over again. There are truly just 3 petals. Oops, there we go. It did start, if you notice, at 0, 0. It did start. Not the 6th petal. Not the 6th petal. Did it start at the polar axis or did it start in the first quadrant? First petal was in the first quadrant. The polar axis, in case you're wondering, is this little guy right here, the positive x-axis. Polar axis. There we go. But this one, as you guys can tell, even though the first petal was in the first quadrant, the key here is the word starting. So since this guy, this polar graph, started at the origin, which is right here, if I can get it to go, and then it started tracing, it started at the polar axis, and then it went ahead and went through its rotation. So that's why we're going to choose letter A. All right, BC kids. I just threw my iPad, but don't worry, everything's good. Those are all the questions that I had you guys submitting on the forms. I might have some AB kids that are just starting to get on to get ready to go. I'm going to start the AB session at 11. I do have the document up, the AB summer packet question document that I did email out that you were able to submit your questions in. And as far as I can tell, I have responses from 7 of you, from Patricia, Kevin, Jonathan, Joseph, Jack, who I called John in the email recently, sorry, Jack, Lainey, and then Thomas. So if any of you other ones were like, what? There's something where we can mark down our questions? Anyway, feel free to go on over and try to fill out the form. But if you don't think you have time, and if there's like 1 or 2 or 3 questions that I really want you to do, AB kids that are just joining us once again, please feel free to just send me a quick email and that'll work also. Okay, so with that, BC kids, we're signing off, except a lot of you did not join us today, so you might be joining us a little bit later. Remember, there is one other study session. I believe it's next. I should have this. Don't worry. I can pull it up really quickly. I can pull it up really quickly. August 6th at 7 p.m. That's right. It's the first day of in-service that night. So it's Monday night at 7 p.m. If you didn't join us today, you can join us then for a live session where you can ask me other questions or new questions, different questions, ask me clarifications, etc. You can email me with those questions, or you can fill out the form, and that would be a little bit easier if it's just one of the questions on the packet. BC kids, since I didn't see any of you guys check in during the actual session itself, you've made it all the way through. In order to get credit for your participation for watching this, please go ahead and email me when you do watch this at a later date with, which did I have you email me with? You can say live study session number 1 completed. And then you can go ahead and put the phrase at the end. I did watch a Mr. Rogers movie recently. So let's go ahead and say it's a beautiful day in the neighborhood. Okay? So BC kids, to get credit, you need to go ahead and email me the live study session number 1 completed if you do watch this at a later date. And then email me the phrase, it's a beautiful day in the neighborhood. AB kids, let me go ahead and get set up with your guys' packet. That way we'll be ready to go. Let me go ahead and turn off the microphone just for a little bit as I get things situated. All right, it's 11 o'clock, so I'm going to start pretty soon on the AB questions I've gotten submitted on the forms. When I was closing out the BC session just a second ago, I did mention about the forms that I had received. Here we go. I'm switching over to AB, sorry. From AB kids. So I got forms from Kevin, Patricia, Jonathan, Joseph, Jack, Lainey, and Thomas. There is another online live session. It's Monday at 7 p.m. So if you aren't able to join us on this one, you might watch it at a later time. And if so, at the end of this or somewhere around the end of this, I will give you guys a way of proving to me that you did complete this video. Or you could watch the online live session at Monday at 7. Or you could watch the Monday at 7 session at a later date. And once again, there'll be another direction given towards the end of the movie somewhere or others during the end of the 1-hour Calc AB session where you guys can once again get credit if you're not able to be there. So I am going to answer as many questions as I can today from what you guys showed me that you did get stuck on, starting just kind of at the beginning of the packet and going all the way through, just hitting the questions that were submitted to me on the form. If for any reason you realize that you had an extra question that you didn't get to submit on the form, I do have my email open right in front of me. So I did have it open in front of me. There we go. So if there's something really quick that you want to show me, I think you can comment on this video also, but I can't promise that I see it just because I think I have to like open up this little control panel-y thing and then see who else is in here and all that jazz. So anyway, if you guys want to email me something really quick, if you have a question, that's totally fine. Just to send me a quick email, and that way I can see it and I can see it coming in and then try to address it right away. But otherwise, let's go ahead and get started on the ones that you guys asked specifically on the form. Let me quickly get my water just because I have been talking for almost an hour straight. So far, though, there are more AB kids than BC kids that showed up, so that's a good thing. Maybe you guys are more dedicated. All right, I have a little bit of water. Make sure you guys have your colored pens ready, because what you should be writing down right now is not penciling in the solution that theoretically you came up with the first time. That's what pencil is for. But colored pen trying to correct, or maybe even another colored pen if you tried to correct it and it didn't work and you're still getting stuck. All right, I have my red pen ready to go. I have the answers, not the answers, the questions ready to go. And the answers to double check the work along the way. So the first question that I see that anyone asked for, one of you asked for number 14, and then two more of you asked for number 15. So let's go ahead and peek at numbers 14 and 15 first. Let's not mark randomly. There we go. Okay, talking about intercepts specifically, finding the x and y intercepts. So one of you asked for 14 and two of you asked for 15. These are interesting functions. We're definitely going to see some interesting functions in Calc AB this year. Not that they're all going to be super hard or weird, but they are definitely not going to be quite as basic as last year. If you hear weird noises, it's just because my dog is interested in what I'm doing and trying to get some attention at the same time. Okay, number 14. Here we go. X and Y intercepts. So from up above, the directions were in the quick little box. X-intercepts at y equal to 0 solve, y-intercepts at x equal to 0 and solve. So we're just going to go ahead and do that really quickly. Let me go ahead and just make a quick little category. So we're looking for the x-ints, looking for the y-ints. For both of these functions, I'm just going to do a quick little table just to make it a lot easier as far as organization, and let's go. Okay, so for the x-ints of the first one, we're going to go ahead and set y equal to 0, so 0 is equal to. If you guys were to read this function, it would be x times the square root of 16 minus x squared times, you can think of factors, and factors we can think when solving for 0, setting each equal to 0. So we would have both from the first one, x equals 0, but from the second one, we'd also have the square root of 16 minus x squared equals 0. Sorry, in my head really quickly I was like, hey, you're also going to have plus or minus 4, but that might have been a little bit fast for a few of you. So if you needed to, you could go ahead and not just think of setting the first one equal to 0, which is super easy, but the second one as well. And then to solve that, you would go ahead and go through just to change up the colors. Not green, it's not Christmas. Patriotic, sure, it's summer. We could square both sides. You would then go ahead and either subtract the 16 or add the x squared plus or minus square root both sides, and you would end up with plus or minus 4. For the y-intercept, as we already said, set x equal to 0. So if we plug in, I apologize, not 0, 16 minus. If it was 0 minus, we'd be in some trouble. Times a real number, which would be 4, which does just end up being 0. So we end up with, if you're thinking about the actual points themselves on the first one, you would get 0, 0. Apologize, x is 4, 4, 0, negative 4, 0. Those are the x-intercepts, and actually by definition, your y-intercept is already in there as well because at the origin it intersects both the x and the y. For number 15, a couple more of you guys had questions there. Once again, we're setting x equal to 0, y equal to 0. First of all, for the x-intercept, y equals 0 squared. And then go ahead and factor, because once again, as we saw in the last example, factoring is the easiest way as far as finding the zeros, because then we can just set each of these little guys equal to 0, since 0 squared is really just 0. So we end up with x equals 0 and x equals plus or minus 2, if that was a little too fast for you. You could have taken this off to the side. And when you had solved, you would have had to do a plus or minus square root. For the bottom, setting now x equal to 0. That one's pretty basic because 0 cubed minus 4 times 0. When you plus or minus square root of 0, you still just get 0. So once again, you're going to have a shared xy intercept. You're going to have the x-intercepts as 0, 0, 2, 0, and negative 2, 0. Making sure my microphone is turned on. I forgot whether or not I turned it back on. Okay, there's our 3 points. And once again, the origin is both the x and y intercept. Double checking our key really quickly. We have 0, 0, plus or minus 4, 0, and 0, 0. Good, that's a check for number 14. And then that's a check also for number 15. Okay, those are the first 2 questions that you guys had asked. Let's go ahead and keep going because there were definitely more. The next questions that I saw, I didn't see any questions on points of intersection, so we're moving on to domain and range. And there were multiple ones of you that asked for number 21. So let's go check out what's going on number 21, because you did not like it. Inverses. Oh, nope, sorry. That's the next section. Domain and range. We're thinking about how far left, how far right, how far down, how far up. The range, or the intervals of x's and the intervals of y's that are allowed. For number 21, this one is actually kind of sad because he's super easy if. This is something we're going to work to develop. I'm circling, sorry, the ones that we're going over today. Number 21 is super easy if you know how sine works. In Calc AB, we're definitely going to be working just to get a more natural understanding of, refreshing the Gmail in case someone's email. Nope, you guys are good. We're going to get a much, hopefully, more natural sense of what's going on with functions just by not just memorizing them for a test and having to know a few of them at a time, but knowing a lot of them. 3 sine of x is definitely one of our basic functions, basic graphs. The most basic one is just normal sine of x, not 3 sine of x. Normal sine of x has the graph of going up 1, down 1, starting at the middle, at the origin, and then every 2 pi completing a cycle. So that's normal sine. So all we have to do is basically just ask ourselves the question, what changes when we have a 3? And hopefully you guys remember from transformations of functions that this is going to be a vertical stretch by a factor of 3, which means instead of going up 1, down 1, now it's going to go up 3 and down 3. And there is no shift, there is no reflection, anything crazy like that. So all it's going to change is instead of going up to 1, down to -1, it's going up to 3 and down to -3. And if you remember, sine's just going to cycle through the periodic graph. He's just going to keep going like a wave that never slows down. So therefore, we can go ahead and say, oh, okay, domain, all real numbers. Y goes forever left, forever right. Range, our y's are going to be stuck in between -3 and 3 because sine is limited. 3 sine of x is limited as such. So number 21, it wasn't so much of a actual solving or plugging into a table. It was more like sine, oh, I know him, and then think about the 3, vertical stretch by 3, and then thinking about how far left, how far right, how far down, how far left. Okay, that was number 21. You guys had some questions on the inverse section. Actually, a few questions on that one. So let me go ahead and touch on those briefly. I'm going to try to get questions in each and every section. I might not cover every single one. Maybe we'll go back to a few, but if I answer a question, I'm like, that should help you on the next 2, I'll move on, and then if there's time at the end, I'll come back to them. So in the inverses section, let's see if we can find a good indicator. We'll check that sine curve really quickly, make sure I didn't do something silly. Domain, all real numbers. Range, -3 to 3. This one, all that was different is I said f of x instead of y, but it's okay, both are the same. F of x is just snazzy function notation for the y. And then this one, if you guys remember, this is another way of writing all real numbers. -infinity to positive infinity, open intervals on both. Okay, so inverses. Basic idea, inverses, reflections across the y equals x line. Things come in like horizontal line test, things come in like whether a function is invertible or not, whether its inverse will be a function or a relation, things come in like switch the x and y, solve for y, etc., etc. So let's see what we can do. I technically have questions on 24, 27, and 28. Okay. 24 is the only one from up above in the problems. Let's go ahead and take him. And then we have 2 concept-y questions on 27, 28. For number 24, if you guys think about him right away, he's going to be a parabola. That 1/3, you might not totally know exactly what's going on with the 1/3, but long story short, he is going to be a parabola that's been vertically shrunk just a little bit. That's roughly what's going on. He hasn't been shifted, so he still has an origin at 0, 0. He's just kind of been pushed down a little bit. So when we go and try to find his inverse, you think about it, his inverse, if it flips across that y equals x line, all of a sudden, his inverse. So that's going to make this guy a little bit tricky. Let's go ahead and check out the directions really fast because he does fail the horizontal line test. It just says find the inverse. It doesn't just say the inverse. It doesn't just say the inverse function. So we will find the inverse. We will go ahead and switch the x and y, even though it's going to be an inverse relation. We will go ahead and multiply both sides by 3. We will go ahead and plus or minus square root. So where it gets a little tricky, because the inverse relation is going to have a positive square root piece and a negative square root piece to be the inverse of the entire function. But as you guys notice, this will fail the vertical line test. It's going to fail because the top branch is symmetric with the bottom branch. So because it's going to fail the vertical line test, well, in that way, we would not be able to call this the inverse relation, or I should say the inverse function. We wouldn't be able to call this f inverse of x. That would be improper. We could go ahead and say, hey, it's our inverse relation, dun, 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 or we could restrict all of this and we could say something like, okay, so the inverse function would only be one branch and not the entire branch. Let's see what I went ahead and did when I was solving this one. I did call it the inverse. I do not like my notation, although I understand why I did it, because it is the inverse relation. Just it's technically not a function. So if you did want to use that inverse notation, go ahead and just choose the principal branch or the top branch. Or if you do want to show both of them, we can't just call it y. The problem being is that's the original notation, but we could say something to the effect of the inverse would be defined by, I guess we never actually used y, did we? If we call it the inverse, though, we're technically being okay because we're redefining the y. Okay, so that was a little bit messy as far as notation, a little bit messy as far as what to do. We would technically have to say that this original function is, if we had a little bit more time, not invertible. or if we were given a bit more detailed directions. Not one-to-one, fails the horizontal line test. But anyways, okay, so that's what's going on with that guy. 27, 28, you guys were asking about those two. This one is more concept-y than anything. If an original function has 2, 7, then what's going on the inverse function? Well, I have no clue about anything else except for this 0.27. I don't know anything else about the original. So we just have to ask ourselves, well, does something special happen with originals and inverses with their points? And hopefully the answer that you guys remember from pre-cal or went back and looked at or will kind of be jogged in your memory right now as I say it, is that the x's and y's switch. And that's it. The x's and y's switch. I apologize, I moved my iPad. And explain how the graphs of f and f inverse compare. We've already talked about that as far as the reflection across the y equals x line. You can check that out in the answer key if you want to know how to word that. Okay, there were a couple questions on the equation of the line section. Ooh, let me go first to number 30. Number 29 is kind of nasty too. So we have questions on technically 29, 30, 34, and 35. I'm marking them that way. I have them down, even if I don't cover them, so I can kind of quickly come back to them. So we have questions on 24, 27, and 20. Okay, so for number 29, what makes these funny is that we have an undefined slope and a slope of 0. Now, actually, I think the slope of 0 one, number 30, is the easier one, although more of you guys had a question on that one. Because if you just think about, well, I have a point and I have a slope, hopefully we're thinking point slope form, right? Y minus y1 equals m times x minus x1. We have a point, we have a slope, let's plug it into point slope. That's what the name is there to help us remember. So we could just plug in y minus y1. We have that little 2 over there. Equals slope of 0, fine, plug in 0. And x minus -4 would be x plus 4. And if you were trying to simplify, we would keep going from there in that we'd have y minus 2 is equal to, well, 0 times anything is 0. I know it's weird, but we end up with y equals 2, the horizontal line. Y equals 2, the horizontal line. What's weirder in the first one is that in the first one, y minus y1 equals m times x minus x1 does not exactly work because with an undefined slope, how do we plug in an undefined slope to m? There actually is a trick, and this is actually kind of nifty. So I'm going to show you the trick. The trick is y minus, we could actually plug this in. A little bit more of a trick, and I don't think it's necessarily super technical in the sense of technically right. Or technically correct, or it's not a very formal show of what's going on, but you could make the undefined slope. Slope of 0 is easy, m is equal to 0. Undefined slope is a little harder because you have some sort of number over 0. That little over 0 is what makes it undefined. You could actually say, I don't know what number is on top specifically with what you're talking about, but I do know it needs to be over 0. But at this point, you're like, how do I solve? Well, I know it's funny, but you could technically multiply both sides by 0. This does get you to the right answer. Because now you end up with, you can actually multiply by 0 over a number if you want. You can cancel out that number. 0 over a number is just going to be 0. 0 times anything is still just going to be 0. 0 is equal to x minus 5. X is equal to 5. Now, we have memorized some things as far as, hey, whenever we have undefined slopes, it's always going to be a vertical line, which is x equals. Whenever you have a slope of 0, it's going to be a horizontal line, which is y equals. You could steal the x, you could steal the y. That's using the concepts, and it's totally valid. But even though it's totally valid, you could use the concepts and kind of jump to the answer, or you could technically plug it into point slope. Okay, those are both weird. I totally agree with that. Remember, this is being recorded, so if you jump in, I see a few of you guys going in, going out. If you jump in, you can go back and see the questions that you need. 34 is super basic in the sense of they give us 2 points. Once again, I would use point slope form. But with point slope form, you don't have the nice slope ready to go. You could just steal whichever point you think is prettier. I like this one because there are no negatives. But the problem is we still need the m. And so to get the m, you would need to go back and say, oh yeah, rise over run. Rise over run says y2 minus y1. You just pick whatever one you want to make. First and the second, just keep the order straight. y2 minus y1 all over x2 minus x1. And pretty quickly you should end up with negative 4 over 4, which is a negative 1 slope. You could go ahead and simplify that to make it nice and pretty. I'm going to go ahead and get rid of this big old arrow because now he's in my way. Remember, if you guys have any questions during the video, just send me a quick email. I have it up and I'll see it. But y is equal to, we have a negative x once we distribute. We're going to have a positive 1 plus 2. If we get y by itself, I'm double checking real fast. But I have negative x plus 3. Booyah! And then x equals 5 and y equals 2. Good. I think one other person had a question on number 35. And I know you might not like it, how it says an x-intercept and a y-intercept. To be honest, we kind of like this y-intercept. You might even be able to cheat just a little bit and go to the old-fashioned slope-intercept form and say, hey, the y-intercept has something to do with the b and then the n. You could totally go that route. In calculus, though, we are going to use the point-slope form a lot. So this is a good chance to practice once again. And you can do the exact same thing that we just did. I'm not going to finish this one, but where you choose one of the points, like we did up here, we chose the point 1, 2. Plug it in as your x1, y1, leaving the y alone, leaving the x alone. But then we had to go ahead and come over here off to the side and use both points in the m equation of y2 minus y1 over x2 minus x1 so that we can go ahead and plug in. And then we just went ahead and simplified and solved. Just in case you couldn't follow, I just saw that that was pretty messy in the sense of I never actually wrote this equation got me negative 1. There you go. So you can plug in these 2 points and you can find the slope, you can find the slope between them just using that same little equation, y2 minus y1 over x2 minus x1. And I think you guys probably see me, or can see me in the answer key, following the exact same steps that I just showed you to solve. Okay, so with that, let's go ahead and move on to a new section. Let me see what our next questions are. Unit circle, good, no questions. You're just filling in. Trigonometric equations. We really didn't like number 40. Okay, so number 40. Trigonometric equations just means there are equations with trig that we need to solve. Number 40, I did give you a clue. Technically, I do have questions if some of you are like, wait, I did submit a question. Okay, questions on these 3. Well, let's go ahead and jump to number 40 since more of you had questions on that one. I think I did get someone else's responses. Thank you, thank you. I will be able to see it as far as updated changes from here, number 37 on. And if I missed anything on the ones before, I can go ahead and cover them in the next study session, unless we have some time or unless I've missed something 1 through 40 and you want me to cover, just send me a quick email. If there's time, I'll cover it. So in number 40, this one said, well, I mean, all of them just say solve. But this one's nasty because you have a cosine squared and a cosine. You're like, oh. But if you were to just rearrange it a little bit, putting the cosine of x, the minus cosine of x before the minus 1, maybe you realize this is very much of the form of ax squared plus bx plus c, where we want to get it into a nice factored form. Now, if you wanted to, you could actually do what we did last year, and you could actually change this form to something prettier. Once again, you totally did not have to, but you could let u equal cosine of x, let u equal that big block that you don't like. You can say, fine, it's 2 blop squared, or u squared, minus 1 blop, 1 cosine, minus 1. And you could try to factor this guy. Now guys, in factoring, I really can't reteach factoring again in Calculus AB. That doesn't mean I can't explain it to you after school again. Or actually, not many of you came in for help on factoring last year. So maybe you need to come in. I did have some calculus kids a couple years ago that came in, asked me for algebra help. That way they wouldn't be behind that year. And it ended up working quite well. Don't be ashamed to let me know that factoring is still bad for you. But I'm not going to be able to reteach it in the midst of us doing calculus. But what we can do real quick here in the summer packet while you're reviewing Remember, we could do a little x and say 2 times -1 is -2. We multiply the outer, or I should say the first and the last. And then we steal the inner. What factors of -2 had to be -1? Well, -2 and +1. And so if you do the x method, you're not going to be able to jump straight to the answer on this one since there is a first term. But what you could do is you could go ahead and keep the first, split the middle into the -2u, stealing from right here, and the +1u, and then keep the last. And then we can do grouping. Pulling out a 2u, we'll end up with a u minus 1. Plus, we don't need to pull anything out from this one, so we could just think of it as 1, u minus 1. If you notice, we have shared factors of 2u plus 1, u minus 1 equals 0. Now, this is on a video, so feel free to pause it or come back to it later and try to think about it, work through it. But what I'm going to do to save on time and to save on space is to go ahead and just take all this away, because that is technically optional. The other way is that you could possibly, depending on how your brain works, you could maybe start to make the jump of looking at the first and saying 2u squared could come from 2u and u. Look at the last. 1 has to come from 1 times 1. Nothing else multiplies to be 1 without using nasty fractions. Then you can check your outer and your inner. I have 2u on this one. I have 1u on that one. I need to get this -u. I need a negative on this guy, which can come from putting a minus on the 1. And then I need a positive on this guy, which can come from putting a positive right there. So we can go ahead and jump and say, hey, it's not a u anymore, it's cosine. So 2 cosine of x plus 1, cosine of x minus 1 equals 0. Remember, we have set each one equal to 0. We end up with, after some quick solving, cosine of x equals -1/2. Subtracting the 1, dividing the 2, and then adding the 1. We also end up with cosine of x equals +1. And on the summer packet, you were supposed to fill out your unit circle. On your unit circle, remember, for each of the ordered pairs, I can show it to you here. There we go. On each of the ordered pairs, remember, cosine for each of these. Cosine is going to be the x's. Cosine of the angle, if you want to switch that, you could switch that. Instead of cosine of x, you can make cosine of theta. But cosine is going to be the x coordinate, whereas sine, let me just change the colors for sake of simplicity. Sine are going to be the y's. So according to this one, we're trying to solve our equation. We're trying to go ahead and think of, don't want to do that. When cosine is -1/2 and when cosine is 1. I don't remember the directions as to whether it was 0 to 2 pi it was. So 0 to 2 pi cosine is only going to be 1 at one place, which is going to be when the angle is 0. If you're to look around the unit circle, x is only 1 at one place, and that's at 0. It is at 2 pi. Let's check out real quick. The reason I'm not including 2 pi is because it says not or equal to. So at 0, and then cosine will also be -1/2 in the second and the third quadrants at pi over 3. Pi over 3 angles, I apologize, I just said pi over 3. And pi over 3 angles in the second quadrant would be 2 pi over 3. And then the third quadrant would be 4 pi over 3. So those would be our 2 answers. For number, if I just messed up, at number 40. There we go. 0, 2 pi over 3, and 4 pi over 3. You guys did have some questions on the other ones. We're going to go ahead and move on because we did the hardest one in that section. And once again, if there's time, we'll come back to it. If not, I can see if you guys still have questions. Pop me an email, and I'll include it on the Monday night study session at 7. Okay, so then moving on from trig equations. Remember, real quick, before I totally move on from here, for trig equations, you're having to go backwards, and you're having to say, okay, when does sine equal -1/2? And the reason why I put both of these in my head, I think of sine as the opposite side of the triangles. And I want negative opposites to be going down, which is in the third and fourth quadrants. Or you can think all students take calculus. Sine is not positive in the third and fourth quadrants. I was thinking down a little, but if you guys, once again, are more just strict memorizing the unit circle, you can look in your table, your cheater chart, or you can look in the circle itself and say, hey, where are the y's negative 1/2? And that would happen at 11 pi over 6 and 7 pi over 6. For instance, for that equation we were just looking at as an example, number 37. Okay, now moving on. Someone did have a question on 37. Let's go to transformations of functions, number 43. I think it's right down here. There's a lot going on, number 43. Right up above, they gave you a quick reminder of how to shift up or down, right or left, and how to reflect. So in number 43, it's trying to have you basically take, let me get back to my video to make sure I'm showing it right. In number 43, it's basically trying to have you take 1 point and 1 point only, not a whole graph, not a whole crazy cosine or sine or something else nasty like an exponential function. Just 1 point and say, if you did these transformations, what would you end up getting? If you did these transformations, what would you end up getting? So, for instance, on this first one, and I might not do every single one, just to give you guys a feel for it though. On this first one, if I, sorry, it's my dog if you can hear him. If I look at this, I would say that this has a vertical shift down 3. A vertical shift down 3. That's what f of x or the y's minus 3 looks like. Now, if I were to actually do that to this point, if it's vertical, well then I'm changing the y's, and if it's down 3, I'm subtracting 3. So I could just say 2 and then 4, take away 3, ends up with the point 2, 1. And as you guys look at the answer key, that's exactly what I did. I tried to say what was going on as far as what the transformation was and then what the new point was. And so each of these has some sort of shift, some sort of reflection going on. Every time there's a horizontal, I'm looking at the x and making a change, and every time there's a vertical, I'm looking at the y and making a change. And maybe it's possible, like in letter D, that I have something where both the x and the y is changing. Maybe it's something like in letter C, where I now have a stretch and not a shift, and so I'm multiplying and not adding. Maybe in letter E, there's something with a reflection, so I'm putting a negative on one of the coordinates. But what I'm doing is I'm thinking of, okay, according to those equations, what is the transformation? What's the transformation? And then I'm saying, okay, vertical, I'm looking at the y and changing it accordingly, either adding or subtracting, multiplying by a negative or multiplying by another number. If it's horizontal, I'm doing all of that to the x depending on the equation. So hopefully that gives you an idea on number 43. It was a little tricky, and yet it's actually kind of simple as long as you correctly identify the transformation. Okay, moving on to vertical asymptotes. We had some questions in there. So what I have on the circle number 43, we only did A. If someone emails me, I might do a few more. But let's go ahead and move on to number, let's see, I have 46 as a question, 48, and 49. Let me see which ones I like out of these ones. Let's just look at number 46 and 48. I think all you're trying to find is what are the vertical asymptotes? Ooh, I see why 49 might be messy. No, I think we're all right. We'll just do 46 and 48. We should be able to answer 49 with that. Vertical asymptotes, remember, we have poles or vertical asymptotes, all that can occur with the zeros of the denominator. The problem is when we have a denominator equal to 0, that's when discontinuities occur. Okay? The bottom will be 0 when we'll take the factors, x squared, 1 minus x. We're setting the denominator equal to 0. That's when we'll get this problem going on, which is when discontinuities occur. Vertical asymptotes, though, quick reminder, vertical asymptotes are also what we call non-removable discontinuities. That's going to be important in a second. It's not actually important for 46, and I'll show you why in just a moment. So I took the denominator for this one, x squared times 1 minus x times, that's factors. Factors set each one equal to 0. Pretty quickly, hopefully you guys get x is equal to 0 and x is equal to 1. And both of those are vertical asymptotes. Now here's what's different in 48 and 49. In 48, when we go to set the denominator equal to 0, it's kind of messy as it is until or unless we factor. So when we factor, we're going to end up with, I believe, x plus 2 and x minus 1. Now if you notice, right away we have 2 shared factors. And a lot of you are like, yeah, cross it out. Okay, that's good. Yeah, cross it out. It is shared, but here's where some people might get confused. Some people might be like, oh, hey, so there must be vertical asymptotes at, and not even notice that it's shared and just go ahead and say x equals -2 and x equals 1. But the problem is we have to take away that x equals 1 for the very reason that we can see up above that the numerator and denominator both have that same shared factor. So if you guys look up above one more time, I just wrote down just a moment ago, vertical asymptotes are non-removable. Non-removable means not shared, not able to be factored out, aka not a whole. There is a discontinuity at x equals 1, but the discontinuity is that there's a whole at x equals 1, and a whole is not a vertical asymptote. So that's why you only had one answer, x equals -2, and not the other one, x equals 1. And that's that quick little note that I tried to write down there below. If you guys notice, 49 is going to have something very, very similar. Okay, we also had questions on the next section, and the next section is horizontal asymptotes, but I only had one question. That was number 51. So number 51, let's go ahead and go peek at that one. You guys should have already peeked at horizontal asymptotes and reviewed how we have degree tests. And with the degree tests, we look at a function. And as we look at a function, we are focusing on the term with the highest degree, which is not the highest coefficient, but instead the x to the highest power. And so the two terms that I see with x to the highest power on number 51 is 5x cubed and -3x cubed. And if you guys notice up above, that would be a case where you have a tie. The numerator and denominator, their degrees tie. And since their degrees tie, this should lead you to what our clue would be, the ratio of the leading coefficients. And so this one, you're going to end up with a horizontal asymptote at 5/-3, which is the exact same thing as y equals -5 thirds. A positive over a negative is a negative. A positive over a negative is a negative. Hence why we're just able to make it -5 thirds. And the y equals is just the horizontal line, which is what the asymptote or where the asymptote would be. Our next question that we have actually doesn't come until properties of logarithms. So we get to skip a couple sections, which is a nice thing because our time kind of is running short, but we're doing on logarithms. Let me circle the ones we have questions on, which are 69, 73, 74, and number 76. Remember, I am recording once again, so if I go too fast on something you have a question on, feel free to send me a quick email. Last year there were people commenting, but I don't know if I see you guys commenting. Yeah, so I'm not sure what's going on, but anyway, if you can figure out a way to comment on this video, you totally can do that too if you have a question, but I figured it might be easier just as far as for later. There not being tons of weird comments on the video for you guys just to email me if something comes up. But here we go. I am taping so you can slow me down later and go back to and listen to your specific questions if I go too fast. I love properties of logarithms. You guys have the review up above. They're like little baby puzzles. I talk about them. Doesn't mean that you like them, but I might go a little fast. But let me at least try to talk through a few of these. I'm going to start with easiest to hardest if you guys don't mind. And I think the easiest one right now that I can see out of all of these is number 73. Because number 73 has log base 9 of 9 cubed. So right now, right here, number 73. Log base 9 of 9 cubed. If you guys remember that cool little property of when the bases match, I can pop down that power in front, and I can just write it 3 times log base 9 of 9. And log base 9 of 9 That's the exact same thing as 1. And this comes back to the property that, first of all, log base A, it's the n, you can pull that n down. That's one property. But if we go ahead and put another little base A, so that those bases match, we can actually go one step further and just call it n. So that was a little bit crazy, and yet it was a little bit easy all at the same time, because you just end up with 3. Bringing down that 3 and realizing log base 9 of 9 just cancels out. Kind of like 9 to the power of log base 9, it just cancels out. The next easiest one I see would probably be number 76, because I could rewrite 76 to be log base 2 of 2 to the 1/2. I know it's a little bit of a stretch, but a square root can be written as a 1/2 power to the 5. And now it's pretty snazzy. You can do this 2 different ways, but one way is you can say, well, a power to a power. I have 2 powers right here. A power to a power, you multiply. And 1/2 times 5 is 5/2. And then we can use the exact same thing we just did in 73. We can pull down this 5/2. We can say log base 2 of 2 is 1, and we end up just with the 5/2 power left. 69, maybe after doing 73 and 76, it makes 69 a lot more clear, because we're also going to change how this one looks, in that we're going to make this 9 to the 1/5. That's another way of writing the 5th root. Once again, some pre-calc and algebraic. It's actually kind of algebra 1, but it is hard algebra 1. A 5th root can be rewritten as a 1/5 power. Now, some of you guys are like, sweet, bring down the 1/5, and you're entirely right. The problem is you can go one step further, and here's the way that you can go one step further. Lainey, I just saw your question come in, so I'll check it in just a second. We can make this 9 match the base of 3. We can make the 9 match the base of 3, because we can say, well, 9 is the same thing as 3 squared. And as soon as we get that 9 broken down into a base of 3, then we can go ahead and say, sweet. Once again, power to a power. We can make 2 times 1/5, 2/5. Remember, when you multiply fractions, 2 times 1/5. We're just multiplying numerators and denominators. We're not adding, we're multiplying. So 2 times 1 is 2, 1 times 5 is 5. So 2 times 1/5 is 2/5. I can bring down that 2/5. And log base 3 of 3, just like log base 9 of 9, just like log base 2 of 2, just like ln of e, ends up just becoming 1, and I end up with just 2/5. All right, those 3 were all super similar. Let me go ahead and check out what's going on as far as, Lainey, your question, 82 or 84. Yeah, thanks for letting me know, and I'll make sure to get to those. We might pop over to those next. Oh, thanks, Lainey. And she's also saying you guys can't comment because your Heritage emails, they must have done some new security, so you can't do YouTube with your Heritage emails. And without being on Heritage, your Heritage Warriors, you can't comment. Okay, that's fine. The emails are working just fine. Where are we at? Number 74. And then let's go check out what questions Lainey was asking about. So number 74, oh, totally different property. It's one up above. The one that has to do with adding. Here we go. We're going to be using this one right here. That you can take an addition of 2 logs with the exact same bases, and you can make it a product. An addition of 2 logs, the exact same bases, and make it a product. So here we go. I have an addition. There are 2 logs, the exact same base. So I can go ahead and say, sweet, let's use that property to go ahead and make it 25 times 4. I have log base 10 of 100. Now some of you are like, I'm done. Ah, look at the answer key. You're not done, and here's why. Can you make 100? Can you break him down to be a base of 10? And the answer is yes, of course, because 100 is 10 squared. Then you can do our snazzy trick that we've been doing a lot. How? Log base, oh, hi, I don't want you. Log base 10 of 10 is just 1. So the 2 comes down. Log base 10 of 10 is just 1. The 2 is left. So logarithms, logarithm properties. They're fun once you know the properties and once you're able to apply them quickly. They're kind of brutal up until that point. But the cool thing is that your guys' questions all kind of revolved around the same thing where you just needed, I think, a quick reminder, and let me just write a little note here, that whenever you have log base A of A to the n, you can always just bring down the n according to our properties. And then log base A of A can always just reduce to 1. And then n times 1 is just n. And that's actually what we used in all 4 of those. All right, let's check out what's next. I have the 82, 84 ones. Oh, perfect. Lainey, it's the next section. So yeah, let's go over to even and odd. I had a question on number 77, but I also had questions on 82 and 84, which I think are the ones you were just asking about. Perfect. So let's go over to the even and odd functions. I'm going to go ahead and skip number 77 just because there were more questions on the latter ones, the 82, 84 without the graph. I'll just give you a quick hint on 77 because remember, check out the origin. Where's the origin? There he is. Here's your y-axis. Here's your x-axis. Let me undo. There's your y. There's your x. And as you look at this graph and as you're trying to trace them and see what's going on, just think, what kind of symmetry does he have? If you look on one side of the y-axis, doesn't it seem to be copying what's on the other side? And there's one of them that very specifically says, hey, if there's y-axis symmetry, you should go with me. Y-axis symmetry, what's on one side is on the other, and that's what's going on with this graph. But let's go down to number 82 and 84. Okay, number 82 and 84, super similar to one of the questions at the beginning that I was doing where I mentioned it's going to be very, very, very helpful to have an understanding of these graphs, of cosine, sine, even like in general what a 5th degree function looks like. But don't worry, we're going to work on that together as we come back in and start getting ready for calculus before totally diving in. That'll be one of the things we work on, is getting a good understanding of the graphs. So number 82, without going into too much detail, a cosine starts at the top, finishes a cycle every 2 pi, usually goes up to 1 and down to -1, but this time he's going to go up to 2 and down to -2 because of that vertical stretch. He's going to have his bloop, 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 there we go, and then bloop, 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 there we go. Oh, hey, this will help whoever had a question on the earlier one that I just gave a hint on, because if you check it out, doesn't what's going on one side of the y-axis match what's going on the other side, and it can keep on going, keep on going? This guy also has y-axis symmetry. And I know it's nasty because some of you are like, I didn't want to have to think about the graph. I wanted to think about plugging in -x, but the graph is so much easier. If you can look at it and say, look at that y-axis symmetry, that must be, dun dun dun, here's the answer, even. Y-axis symmetry is always an even function. Now, you could memorize a property that says anytime you plug in a -x into a cosine, it does always end up staying the same, but that's the problem, is that needs you to memorize a property, or that needs you to go to the unit circle and see, hey, if I was to in the unit circle go up 30 and go down 30, the cosines are the same. That would require more, I would say, more mental gymnastics. This idea and this way of solving would require a whole lot more work than just being like, I know what cosine looks like. And that's going to help us on number 84, because if you know what cosine looks like, going up 1, down 1, repeating every 2 pi. Well, hold on, we have to think about, well, wait, this guy did change. He didn't get stretched. He got shifted down 3. And if he got shifted down 3, well, instead of going around the x-axis, now he's going to go around. That was actually a sine curve. I apologize. That would be a cosine. Anyway, instead of going around the x-axis, he's going to go around 1, 2, 3. His sinusoidal, I know, but it's not a big deal. His sinusoidal axis, his equilibrium, where the wave is going around, is going to be down at -3 now. So he's going to go up 1 from there and down 1. And he's still going to repeat every 2 pi. That didn't change. All that changed is where it was happening. So he's still going to repeat every 2 pi, but now he's down here cycling. Now, if you guys check this out again, but wait a minute, doesn't what's going on one side of the y-axis still copy what's going on the other side of the y-axis? So once again, both of these have y-axis symmetry. That has not gotten messed up. So once again, we can call this function even. Lainey, hopefully that helps. You weren't the only one that asked about those. A couple other people did as well. So that's with our even and odd. The trig were probably the nastiest ones because they were actually kind of like even odd properties that you could memorize, like I was talking about right here, that would have helped you. But I think if at all possible, if you can visualize that graph, seeing the y-axis symmetry could be a whole lot easier than having to memorize those other properties. Okay, moving on to another section because we do have other questions. Complex fractions. Somebody didn't like 85, 86, or 87. Okay, we only have 5 sections left, and I only see, I think, some good questions here at the beginning of complex fractions, the first 3, and then some good questions at the beginning of the next one, simplifying expressions. So we got a little bit confused by the algebra, a little bit confused by the simplifying. I'm not going to do all 3 of these once again for sake of time, but also to give you guys a few ideas to think about. But I will do one of the complex fractions. Then I'll do one of the simplifying expressions, see if that helps, and then I'll cover the other questions and whatever new questions have been added on Monday night at 7. Remember, that will be recorded for anybody who can't join in then. It will be recorded. You can go back and look at the questions, or the answers, I should say, to other questions that I didn't get to today. But I also want to talk really quickly about the last 2 sections where the videos have not been very nice and happy and working for you guys, and how you can still answer those questions even if the calculus tutorial phobe does not work for you. So complex fractions, first of all, let's cover one of these. Let's see, the worst one. They're all kind of similar. Maybe I'll just go with number 87 because he has a lot more, not a lot more, but he has a little bit more going on. But I will show you what I would do for each of them, just in the sense of I would, my trick from last year, I would multiply top and bottom by the common denominators. I put this guy over 1 just to make it a little bit easier. I would put little parentheses so I wouldn't forget to distribute. This guy I would multiply top and bottom by x plus 2 over x plus 2. Don't forget your little parentheses. You do have to distribute on top and on bottom. And then 87, that's the one that I'm going to focus on. So let me go ahead and get a little more room right here. I would multiply by 2x minus 3, 2x minus 3, once again, looking at there's only one denominator, only one trapped denominator. It's in 2 places, but there's only one. That's a little bit easier. If there was more than one, I'd have to multiply by both. What I'm going to do is take this whole thing, the 2x minus 3, the whole lump, and I'm going to multiply him into the 4 and to the 12 over 2x minus 3. Same thing on bottom. I'm going to multiply that 2x minus 3 in next to the 5 and next to the 15. So on top, if you want to think about it, I can keep on using black to separate my fractions. On top, I'm going to have 4 times 2x minus 3. And if you want to write it, if it's easier to you, that's okay. 12 times 2x minus 3 over 2x minus 3. The reason we like this is every time, if we do it properly, those little trapped fractions will disappear. Not disappear as in magically, but disappear as in be simplified out. On bottom, we'll get 5 times 2x minus 3 plus, if it helps you to write it out, 15 times 2x minus 3 all over 2x minus 3. But once again, if we did it right, haha, it's all gone. So then what we get, I'm going to go ahead and do a quick distribution to get rid of these. 8x minus 12 minus 12, that's our numerator. So we went here, and now we're going down here. So 4 times 2x minus 4 times 3. Now on the bottom, 5 times 2x is 10x. 5 times 3 is 15. Not plus 12, sorry, plus 15. Those end up just canceling. Then we end up with 8x minus 24. all over 10x. After some simplifying, you guys hopefully would realize that you could go ahead and pull out a 4 from up top. And the 4 would end up actually, I'm just going to do it right here. I would get 2x minus 6. I could pull out a 2 also, if that makes it any nicer to you. I could pull out a 2, and that'd be x minus 3. The 8 and the 10 can reduce to be, I'm sorry, it's not 1 in anything. 2 goes in 4 times, and 2 goes in 5 times. And we'll end up, just after some simplification, getting 4 times x minus 3 all over 5x. There might be different ways of writing that. You can check out the answer key. But that would be the procedure of, I'll just stay here for now for sake of time. That would be the procedure of simplifying that puppy down. Is finding that trapped denominator, multiplying top and bottom, not forgetting you're distributing, and then carefully simplifying. And there is no shame in writing it out and getting rid of those denominators. That might make a lot more sense for some of you. So I think that was probably, it's at least an indicator as to how to do 85 and 86. Let's go over and peek at the questions you guys had on simplifying expressions. One of you or multiple of you just didn't like 90 through 94, these first ones, and it all had to do with exponents. Let me peek at which one I think is worse. Off top of my head, well, they're all pretty unique. You might want to come back, and we might start here next time on Monday at 7. That way, some of you don't have to wade through at the very beginning. We might work our way backwards, which might be kind of helpful Monday at 7. But let me go ahead and just peek at, let's start with number 92. With number 92, what I see in my head is I see 3 different types of things. I see just coefficients. I see x's. And I see y's. And with division, we can think a few different things. First of all, for numbers, we can just think reducing. So I can say x goes into 12, or sorry, 6 goes into 12 2 times. 6 goes into 18 3 times. So I can start my answer with a 2 and a third. But then I need to move on from numbers and say, okay, well, 12 over 18 is 2/3, but then I have x to the negative 3 and x to the 1. I could actually go ahead and I could do a couple things. One thing is I can remember that when I'm dividing like bases, I subtract their powers. So you could get something like x to the negative 3 minus 1, which would be x to the negative 4. That's one way of putting both of those pink x's together. I could do the same thing with the y's, and y to the 2 minus negative 1 would be 2 plus 1. That's one way. We wouldn't leave the answer like that, though, because negative exponents do end up belonging in or needing to be reciprocated. That's not really a word, but needing to be flipped in the sense of x to the negative 4 belongs down in the denominator. So we would move the x to the 4th. The negative just meant, oh, no, the x to the 4th belonged down in the denominator instead. So that would be our final answer. Some of you might have instead wanted to move this negative 1 up. And then you could have added the exponents, moved the negative 3, the x to the negative 3 down. Once again, added the exponents. There were a couple different ways of doing it, but that's one way of thinking about it. I can tell that some of you guys are confused in a few different things. Like for 91, you can think of when you divide by a fraction, you multiply by a reciprocal. So some of you might be able to figure it out if you rewrote that a little bit nicer. Number 94, you might have liked it if you rewrote it. You might have liked it a little bit better. And you can rearrange multiplication, which might make things a little bit better also to help you think it through. So sometimes just rewriting, sometimes just rearranging makes all the difference. Number 93, you could have rewritten 15x squared all over 5x to the 1/2, and then done the same trick that we just did in the sense of, like, hey, just think about the numbers, start your answer off, then just think about the x's. Remember, you can subtract their powers. That might help a little bit. On number 90, you probably just didn't like it because they were different denominators. Sadly, the only way to get rid of this one or to simplify this one is to say, fine, I have to multiply by the other denominator because they don't match. And fine, I have to multiply by the other denominator because they don't match. Okay, we got through all the sections up until the last few, the limits and a little further in. Just in case some of you guys can't make it Monday, or if you want to make it just at the very beginning of Monday, I will work my way backwards. And so I'll start with these questions here at the very end, which I'm circling right now, which is 16, 19, 22, and 24. For those of you guys that are like, the videos aren't working, last year more people were able to get to them. This year, I think maybe just with different devices updating and maybe the website not being updated. I mean, you guys have probably known that with apps. Some people don't have some developers don't have the desire or even the ability to update. His videos, I think, are working even worse. So what the advice that I gave some students that already emailed me were to go ahead and just use Khan Academy as far as his lessons on limits and his lessons on, let's see, the intermediate value theorem and the basic derivative rules, to try to answer as many as you can. And then as I go ahead and start the Monday's night session, I'll start here, right here at the very end. You guys can feel free to email me also if you're like, you know what, this one problem, I watched Khan and I know the general idea, but I'm just not sure how to answer this question. That's totally fine. And that's something to, at the very end of the packet, if no one's able to, or a lot of you still aren't able to get to the videos, they don't load for you as far as the website that's supposed to be working. That's totally fine. We're actually going to have a day and a half to go over final clarifications. And so we'll start here at the very end of the packet too. For you guys to go ahead and get participation, since you weren't able to comment on the video as Lainey was explaining, go ahead and just email me whether you're watching this now or whether you finish this one later because you weren't able to watch it live. Email me with a quick online study session number 1 completed. Go ahead and you can either do it in the subject line to my email, or you can go ahead and put it in the body of the email. Online study session number 1 completed. And then I made BC do something a little bit different for today for you guys. Let's go ahead and I just watched Mr. Rogers with my family the other day, so why don't you go ahead and write after online study session number 1 completed, won't you be my neighbor? And that will go ahead and get you credit for watching this study session. Remember, you only have to do one of the study sessions, but if you do have other questions that you want clarified, or if you just want to pop into the Monday night one, whether it's live or whether it's after the fact, because they're going to be recorded, to figure out the last few questions that you might have, that's totally fine. If you want to add any other questions, go ahead and just email me. So I think a lot of you guys that are on here already did the online forms. If you have any additional ones, go ahead and just email me and I'll cover that Monday as well. Hope you guys are doing awesome. Hope you enjoy. You have a little more summer than I do because I start in service on Monday. But I'll connect with you or your classmates on Monday night. So I'm going to go ahead and sign off. Thanks for coming. Thanks for attending, and I'll talk to you guys later.